Quantum mechanics, the theory governing the microscopic world, often feels counterintuitive. Particles don't follow defined paths, but exist in a haze of probability. The Feynman path integral formulation offers a powerful way to visualize this strangeness. Imagine a particle traveling from point A to point B. Instead of a single path, quantum mechanics allows for an infinite number of paths. The particle, in a sense, explores all possible routes simultaneously. Each path contributes to the final probability of finding the particle at B. Some paths are more likely, others less so. The path integral sums up these contributions, taking into account the strange rules of quantum interference. This approach, while mathematically complex, provides a useful framework for understanding photon behavior. Photons, the particles of light, beautifully illustrate quantum weirdness. They can exist in a superposition of states, simultaneously being in multiple places or having multiple properties. How can a single particle be in multiple states? One intriguing possibility involves the Higgs field, the energy field that gives particles their mass. Imagine the Higgs field as a vast, undulating ocean of energy extending throughout the universe. Within this ocean, energy can fluctuate, creating ripples and waves. These waves, existing in 4 dimensions, 3 spatial and 1 time, can interfere with each other, much like waves on the surface of a pond. This interference creates complex patterns of energy density within the Higgs field. These energy patterns, we propose, underpin the phenomenon of photon superposition. A photon doesn't exist at a single point in the Higgs field but is instead spread out as a wave function. The wave function represents the probability of finding the photon at a particular point in space-time. The superposition of states arises from the complex interference patterns of the underlying Higgs field energy waves. Consider the path of a single photon as it travels through space. In our model, this path isn't arbitrary but represents a specific energy configuration within the Higgs field. The photon, in a sense, surfs on these underlying energy waves. Each possible path the photon can take corresponds to a distinct energy state within the Higgs field. This leads to a fascinating possibility. Each photon with its unique energy signature might be considered a microcosmic universe. Just as our universe has a specific energy configuration, so too does each photon within its own tiny domain. The different possible paths a photon can take are akin to the different possible histories our universe could have experienced. Section 4. The Neural Big Bang Consciousness and Photon Absorption. Now let's bring consciousness into the picture. Our brains process information through intricate networks of neurons. These neurons communicate via electrical and chemical signals. But what role might photons play? We propose that the absorption of a photon by a biological photoreceptor, such as those in our eyes, triggers a neural Big Bang. When a photon interacts with a photoreceptor, its superposition collapses. It transitions from a state of being in multiple places at once to a definite location. This collapse, we suggest, releases a burst of energy within the photoreceptor. This energy isn't merely thermal, but is structured and organized by the specific energy signature of the absorbed photon. This energy release triggers a cascade of neural activity, a big bang of information processing within the brain. The specific pattern of this neural activity is determined by the unique energy signature of the collapsed photon. This model provides a tantalizing link between the quantum world of photons and the biological processes underlying consciousness. Section 5. Bridging the Gap, Quantum Mechanics and Consciousness. The idea that consciousness might be linked to quantum phenomena is not new. However, our model offers a specific and testable framework for exploring this connection. By considering photons as microcosmic universes and their interaction with biological systems as triggering neural Big Bangs, we open up new avenues for research. Future experiments could investigate the energy signatures of photons absorbed by photoreceptors and correlate these signatures with the resulting neural activity. Advanced imaging techniques might even be able to capture the real-time dynamics of these neural Big Bangs. While much work remains to be done, this speculative framework provides a potential bridge between the enigmatic realms of quantum mechanics and consciousness.